Okay guys, we're going to be taking a look at some equilibrium concepts here. I'm going to split the equilibrium material into two different videos. This first one is going to cover qualitative aspects where you're not really doing any calculations. The next video will cover the quantitative stuff. Now, in the OpenStax book, this is chapter 13. These notes here, these recommended problems were from an ancient textbook we used to use. But anyway, quick look at equilibrium, which is probably the main concept in this entire class, is equilibrium. Okay, so chemistry is all about making a product. Hopefully you've come to realize that. So how do you make a product? Well, you start with reactants, also known as starting materials, or sometimes they're called reagents. So you take your starting materials or your reactants and you turn them into products. Now, they're transferred into products by a forward reaction. Something we don't usually think about in Chem 1 is once you start to build up some products, it turns out products can be transformed back into reactants. So products can turn back into reactants. When you first start a reaction, hey, there aren't any products around. When you first start your reaction, all you have are the starting materials. They turn into products. You start to build up more and more products. The products start to break down into reactants. At some point, you reach what's called a dynamic equilibrium. I know it sounds like an oxymoron. Dynamic makes it sound like something's happening. Equilibrium makes it sound like nothing's moving. So again, you end up with a dynamic equilibrium. And the idea here, equilibrium means, guess what? The concentrations of everything are constant. The concentration of the products isn't going to go up. It's not going to go down. The concentration of the starting materials doesn't change. So all the concentrations remain stable, hence you're at equilibrium. The concentrations are not going to change. You're at equilibrium. Well, what's with the dynamic thing? Guess what? Even though on the macroscopic level it looks like nothing's happening, it looks like you're not making any more products. Hey, guess what? The reactants are constantly turning into products, but the products just as quickly are turning back into reactants. So if a certain number of reactant molecules turn into products, but at the same time these turn into this, the overall concentration does not change and you are at equilibrium. Dynamic because, yeah, the forward reaction, the reverse reaction, they're still taking place, but they're taking place at the same rate. So externally, it doesn't look like anything's happening. Okay, so the big concept here, the qualitative aspects of equilibrium, are all embodied in what's called Le Chatelier's principle. Le Chatelier's principle says once a reaction hits equilibrium, once it's reached equilibrium, you can mess with it. You can disturb the equilibrium. You can force the forward reaction to dominate, and then you'll end up making more products. Or you can force the reverse reaction to dominate, and you'll start making more starting materials. So you can take the system that's at equilibrium and you can push it around a little bit. You can do that by either adding or removing stuff. You can add products, you can remove products, you can add reactants, you can remove reactants. Once you add or remove something, suddenly the whole system starts to shift and it starts to establish a brand new equilibrium position. Now, the thing to understand about Le Chatelier's principle, the types of questions you're going to get will be, hey, if I do this to the reaction mixture, will it make the forward reaction go, or will it shift the reaction back to the left? Will it shift the reaction to the right, or will it shift the reaction to the left? That's the sort of question you can anticipate. Here's the bottom line with Le Chatelier's principle. Whatever changes you try to make by adding or removing stuff, the reaction is going to fight you. So if I try to add more product to a reaction system, that reaction is going to try and burn that product up. I keep adding more product, it's going to want to get rid of the product. If I add more starting materials, more reactants, the reaction is going to shift to the right in order to try to get rid of those reactants. Now, before we get into some specific examples, here's a little quirk of Le Chatelier's principle that you just have to accept at face value. If your reaction is dealing with a liquid or a solid, if you had something in your reaction mixture like copper with a little s, that means solid copper. Guess what? Adding more solid copper doesn't do anything for you. It will not shift the equilibrium. So pure liquids, pure solids have no effect on the position of the equilibrium. There's different ways of explaining this. People will talk about, the concentration of the pure liquid is unity, or the concentration of the pure solid is an invariant concentration. Best to not lose sleep over that. Just trust me on this. If you have an equilibrium system and one of the reactants happens to be a solid material, and you add more solid material, it has no effect. However, anything that's a gas or anything that is aqueous matters. So if you increase the concentration of an aqueous material, that's going to shift the equilibrium to either the right or the left. You increase the concentration of a gaseous material, that will shift the equilibrium to the right or the left. Quick examples here. Applying Le Chatelier's principle, this reaction here, a very famous reaction, I'll be honest with you. To me, this is boring old industrial chemistry. This is the reaction that's used to produce ammonia, NH3. Pretty cheap stuff, ammonia. Might not be the most interesting reaction in the world. At least I never thought so, and then I learned a little bit more about it. This reaction is used to produce ammonia using atmospheric nitrogen. 80% of the air you breathe happens to be atmospheric nitrogen. Turns out plants love nitrogen. Plants grow crazy if you give them enough nitrogen. Well, plants are sitting in the middle of the atmosphere, which is mostly nitrogen. Plants can't use this stuff. They can't use atmospheric nitrogen. If you take that atmospheric nitrogen, turn it into ammonia, that ammonia is used as a fertilizer. So this reaction is really hard to pull off. Back in the early 1900s, forgive the little history lesson here, but the early 1900s, a very famous chemist, Fritz Haber, discovered how to make this reaction work. And they started to actually produce ammonia synthetically. And interesting little thing here. You might think, why do we care about ammonia? Because ammonia can be turned into fertilizer, which can be turned into food. If you take a little look at the world's population, I know this is a chemistry class and all, but here's the world population from about 1750 to about 1900. It doesn't go up very much. The Haber-Bosch process, and it was Fritz Haber who's really credited with developing this process. It comes into being right about here, early 1900s, 1915, 1918, something like that. So here's where they start to make artificial fertilizer. Right here. They start to make it, and you start to see the world population creep up a bit. It wasn't really until after World War II, about 1950, that they really started to mass produce fertilizer using the Haber-Bosch process. So right about here is where they really start to go crazy and just make tons and tons and tons and tons of fertilizer. And look at the world population. Straight up. Most of us would not be alive if it weren't for this reaction. It's absolutely amazing. About 2% of the world's energy production, 2% of all the energy we use in the world goes into making this one product, because this product turns into food. Anyway, so you have this reaction. Everything's gaseous, so you don't have to worry about that. A little bit about ignore pure liquids, ignore pure solids. Everything's a gas. So let's say you're running a factory that makes ammonia with this process, and you have all these things together. One thing to keep in mind when you're thinking in terms of equilibrium, something I noticed over the years. I get students that picture this as two different containers, like there's one container of this and one container. No, all these exist in the same container. You have one reaction vessel, and that reaction vessel at some point is going to be filled with some mixture of all three things. It's hit equilibrium. The concentration of these three things is not changing. It's at equilibrium. So let's say you're there. You have this mixture of these three things in one container. That's your reaction mixture. Let's say we add more nitrogen to it. We just pump some extra nitrogen gas in. So I'm adding more of this. I'm taking the concentration of this and I'm increasing its concentration. Well, is the reaction going to shift to the right or the left? Whatever change you try to make, the reaction is going to fight you. So if I try to increase the concentration of nitrogen, the reaction is going to try to decrease it. How can the reaction decrease? Oh, the reaction can decrease it by shifting to the right. If the equilibrium shifts to the right, that means it's burning up nitrogen. It's using nitrogen to make more ammonia. So if I pump more nitrogen in there, I increase the partial pressure of nitrogen, the equilibrium will shift to the right. In other words, the forward reaction will speed up. It'll hit a new equilibrium mixture. It'll come to equilibrium again. And in that new equilibrium mixture, the concentration of ammonia will be higher. And let's face it, I put that extra nitrogen in there. It tried to get rid of it by turning that extra nitrogen into ammonia. So I end up with a higher concentration of ammonia. Hey, as this stuff turned into ammonia, that used up some of the hydrogen. So the concentration of hydrogen will be lower than in the original equilibrium mixture. So that's the Chatelier's principle. Whatever I do to that system, the reaction is going to try to counteract what I do. So if I increase the amount of nitrogen, the reaction is going to try to decrease it. And again, the only thing the reaction can do, the reaction only has two choices. It can shift to the right or it can shift to the left. That's all the reaction can ever do. So let's say I've got my system and it's at equilibrium, and I do something to remove hydrogen gas. I know, how do you do that? Trust me, we have ways. So pretend I could reach in here and start plucking out hydrogen molecules. So I'm removing hydrogen. If I take this hydrogen away, the reaction is going to try to put it back. If you're the reaction, how can you replace that hydrogen? Oh, you can shift to the left. So if I remove hydrogen, the reaction will shift to the left. That will result in the concentration of nitrogen. Hey, if it shifts to the left, the reaction's shifting to the left, it's replacing some of that hydrogen, and guess what? It's also making more nitrogen. The concentration of the nitrogen is going to go up. Concentration of ammonia is going to go down. Hey, real quick, as we start to go through notes like this, you'll see that I have these notes like I just filled out. And in my note packets, you'll have the exact same notes with all the stuff scribbled on it. So if I send you a PDF with a bunch of notes, you get both the blank notes as well as, if you scroll down enough, you see the notes with all the stuff filled out. That way, if you don't want to listen to the videos, it'll save you some time. Okay, let's continue on with Le Chatelier's principle here. There's some other factors besides concentration that can affect the position of the equilibrium. So you can push this reaction to the left or to the right, not just by adding or removing chemicals, but you can push it around using energy, using thermal energy, changing the temperature of the system. So this reaction here, your nitrogen reacts with your hydrogen, it makes your ammonia. Here's your enthalpy of reaction, your delta H. That negative sign means it's an exothermic reaction. So a negative delta H means it's exothermic. What's that really mean? It means heat is a product in that process. So anytime you get a question about will the reaction shift to the right or the left and it's involving heat, the way to handle that question is you look at that sign of delta H and you rewrite your reaction. This reaction is your nitrogen plus your hydrogen, and they react to produce ammonia, and the other product is heat. So heat is a product of that reaction. I didn't balance this, so let me do that. So heat is a product. So let's say I have this system at equilibrium. I've got all three of these things together. And again, the way to think of this is you got all three of them in a container. All three of them are in a container together. They've reached equilibrium. The concentration's not changing. And I decide to heat the system up. I'm heating the system up. I'm adding thermal energy. I'm adding this product, right? If I add this product, the reaction is going to try to get rid of it. So if I try to get it hotter, the reaction is going to try and get rid of that heat. How can it do that? By shifting to the left. Oops, I forgot to put my other arrow there for equilibrium. So heating the system will shift the equilibrium to the left. And so the concentration of hydrogen, it's going to increase the concentration, because if I shift to the left, I'm making more and more hydrogen. And it will also increase the concentration of, it'll decrease the concentration of ammonia. So anytime you have a problem where it's talking about heating or cooling the system, rewrite the reaction showing heat as either a product, or if it's an endothermic reaction, heat's a reactant. You will have reactions where heat is a reactant. This particular one, heat is a product. Okay, last little thing to look at here for Le Chatelier is what if we change the pressure in the reaction vessel by compressing the gas mixture. So for this particular one here, this particular example, I'm just going to go to my filled in notes here so I don't have to duplicate the drawing. Let's say we've got our reaction mixture, we've got our nitrogen gas, our ammonia gas, our hydrogen gas. They're at equilibrium, and let's say it's in a cylinder here, and here's a piston. So this is a piston that I can push down. I can push down on this, and I can compress this, make the space smaller. If I make this space smaller, I'll of course increase the pressure. So what happens if we raise the pressure? How do we analyze these again? Oh, whatever I do to the system, the reaction is going to try to do the opposite. So if I try to increase the pressure, the reaction is going to try to decrease the pressure. So I'm pushing on this piston, I'm increasing the pressure. You're going, well, how can the reaction change the pressure? Oh, you know what? I'm raising the pressure. It wants to get rid of some of that extra pressure. Hey, if it takes 4 moles of a gas, and keep in mind these are all gases here. So I take 4 moles of a gas and turn it into 2 moles of a gas, I'm going to lower the pressure. So if I increase the pressure, I'm raising the pressure. The system's going to want to lower the pressure. And to do that, it's going to shift to the right. It's going to try to take this 4 moles of gas and turn it into this, which is 2 moles of a gas. So as I increase the pressure, the equilibrium will shift to the right, and I'll end up making more and more ammonia. Indeed, when they run this reaction, they run it at very, very high pressures to try to push that equilibrium to the right and make more and more product. So anyway, that's Le Chatelier's principle. That's the first part of equilibrium, the qualitative part. My next video, I'll continue on with this packet of notes, and we'll be talking about the quantitative stuff, where you start doing some heavy number crunching.